Hi everyone. This lesson is about finding stationary points, and I have a cubic polynomial function here that I'm going to work with. So the first step in finding stationary points is to take the derivative dy dx. In this case, it will become 3x squared, subtract 6x, take 9. Now we will let the derivative equal 0. We know the gradient of the tangent is 0 at a stationary point. And of course, dy dx tells us the gradient of the tangent. Let's take a common factor of 3 to make life easier. So that's a monic quadratic, which would factorize into the form x plus a number and then x plus or minus a different number. Our two numbers for a monic, we need to have numbers that will multiply to equal the negative 3 and add to equal the negative 2. So the numbers we're looking for are negative 3 and positive 1. Those two numbers multiply and add to give the parts we need. So now by the use of the null factor law, we could say that x equals negative 1 or x equals 3. To find the corresponding y value, we substitute into the original function. So what does this imply? Well, if we substitute negative 1 into the original, so the original function, remember, is this one back over here. That's the one that's actually going to be drawing our sketch or our graph. Minus 3 times negative 1 squared minus 9 by negative 1. And that would be negative 1 minus 3 plus 9, which is 5. So our first stationary point is x negative 1, y equals 5. What about the next one? We would end up with 3 cubed minus 3 by 3 squared minus 9 by 3. That's 27 minus 27 minus 27, which is negative 27. So our second stationary point has x value 3, y value negative 27. Now, this is I suppose, the important parts here, the x coordinates of these. How do we determine the nature of these stationary points? Well, we do a calculation of what the derivative behavior is. So we're interested in what the derivative is doing nearby to those stationary points. So my first stationary point was at negative 1. I'm going to go a little bit to the left and a little bit to the right of that and investigate. Now, I'll just rewrite my formula. In fact, any of these formulas here are really my derivative. I've just rearranged them algebraically, haven't I? So I might work with that last one. I'll just write it down over here. dy over dx, it's 3 times x take 3 times x plus 1. Now, if I substitute numbers into that formula, it's just the same as substituting into the quadratic at the top there. Just numbers are a bit smaller, so my life is a bit easier. And when I do substitute those numbers, negative 2 substituted into this gives the value 15, negative 1 gives the value 0, and 0 gives the value negative 9. Those numbers represent the gradient. So a positive 15 means the graph is rising, 0 means the graph is horizontal, and negative means the graph is falling. That stationary point certainly looks like a local maximum. Now let's move over a bit to the next stationary point where x equaled 3. And again, a little bit to the left and a little bit to the right. If I substitute the number 2 into my derivative equation, I get an answer -9, 0, and 15. So this time the graph is going down, then level, then going up. It's pretty clear to me that the stationary point at 1, -5 is a maximum, and the stationary point at 327 is a minimum. Now let's see how we can use our graphing calculator to check that. So here's my graphing calculator. You can see I've typed the original function here, and I've graphed it. It's a cubic polynomial. There's 2 stationary points. Now I can do gsolve and then maximum, and it identifies this point here at the coordinate -1, 5, just like we thought, and it's definitely a max. I can do gsolve minimum, and it finds me this coordinate 3, -27, definitely a minimum. To see the tangent, we can use the sketch button and we can press tangent. Now I can just use the arrow key to move, or I can put an x coordinate as an input and it locks straight onto there. Clearly at this point, our tangent line is horizontal. So that's why our derivative value is 0. And likewise, if I put x equal to 3, same thing over there at the local minimum. Okay, that's enough for this lesson. Thanks for watching.